It's very exciting to see everyone here. Lots of folks joining in. Excellent. So Saadia is a PhD student at the University of Washington. She works on natural language understanding and generation. And she's done some really exciting work on toxic language detection and text generation, and in particular on detecting of implicit social biases in text. Her ACL 2019 paper I know very well. It deals with racial bias in hate speech detection. So not just in hate speech, but in detecting hate speech. Can there be racial bias in such detection? That line of work has had several papers. It's won a lot of awards, been very well received. There was a Best Paper Award. Another of the results was nominated for a Best Paper. So really exciting pieces of work. More generally, she works on machine learning and deep learning techniques for understanding social common sense in logical reasoning in text. So I believe that's the topic of today's talk. And also I believe, but maybe she'll let us know, hot off the presses, this work has been accepted to AAAI 2021. So I think that's really exciting. So on that note, we're really excited to have her here at UMass. Of course, it's virtual, unfortunately, but she has been to UMass before. She's in fact from the area and hopefully knows us well. And we do hope that after the pandemic ends, she'll be able to come and visit and talk to us in person again. So let's all welcome Saadia, and I very much look forward to the talk.
Hi, everyone. Thanks for the introduction. All right. So I'll be presenting this talk, Social Common Sense for Social Good. In particular, I'll be diving into how we can use social common sense reasoning for better narrative understanding, and how this can be used as a powerful tool for equitable and nuanced detection of online toxicity, as well as uncovering instances of disinformation. When reasoning over narratives, key questions that might arise are around the ordering of events that occur in the narrative, as well as interactions between characters and social dynamics between characters, for instance, who did what to whom, as well as predictions about outcomes and motivations, as well as intentions of characters. And when we talk about common sense knowledge, then this usually refers to implicit knowledge relating to social behavior or changes in emotional states, as well as facts about properties of the world and objects, including physical common sense grounding, like the fact that elephants are larger than mice. This knowledge is generally held to be known by all people or a majority of people, and can relate to causes and effects, like for instance, the statement that person X repels person Y's attack, coming with the implication that person X is angry at person Y. So when we think about sentences in a narrative, we rarely think about these sentences in isolation. Instead, we consider them as part of a broader narrative context. For example, when considering one sentence selected from A Tale of Two Cities that refers to both countries, it's not clear just looking at that sentence what two countries are being compared or what the implications are of this comparison and what the author is trying to convey. Prior work on common sense inference focused on phrase level and sentence level reasoning, including the recently proposed comment model. And in this kind of setup, given an example phrase like person X arrived in Boston, then a knowledge inference model would be able to predict, for example, what the person would want to do next upon arrival, or that Boston's at the location Massachusetts. However, when we consider a full narrative, then these sentence level inferences might not make sense given prior knowledge provided by the narrative. For example, if we have the narrative saying a man wanted to make a delicious fruit salad, after a quick run to the store for groceries, he decided to start with strawberries. As he was pulling out a knife, then a phrase level common sense model will predict for that last line that the man wanted to kill someone, but we know this isn't actually what's implied here. This is talking about him wanting to cut strawberries. And this is due to statistical bias in data sets where there's more instances of knives being used for violence So we end up in this situation even where we have a benign context that it predicts the more violent outcome. Another example is Jordan's faucet was broken. She turned on the faucet. Here, the Comet knowledge inference model with the atomic knowledge graph predicts that she'll want to wash her hands or she'll want to turn off the water. However, we know that the faucet's broken, so these kinds of inferences are less plausible. So common sense inference over narratives poses a number of additional challenges over phrase level inference, including plot twists and added information where common sense inferences for a single sentence might be contradicted by earlier or future events in the narrative, relevancy issues where common sense inferences for a more ambiguous sentence in the narrative might be less on topic given the full narrative, co-reference resolution issues where we have to track these complex interactions with characters over a full narrative, including the main character or agent and the secondary characters or patients, which we'll refer to as person X and person Y in this talk. And there's temporal appropriateness issues that arise where phrase level models might generate inferences that don't respect ordering of events in a full narrative. So going back to the earlier example, talking about Jordan's broken faucet, if we have paragraph level inference, then we're able to predict correctly that she'll want to fix the faucet or she'll want to clean up the mess instead. So how do we do this? How do we model plausibility across a full narrative? For that, we worked on coming up with a distant supervision framework that aligns narrative text with knowledge graph of common sense. And we use this distant supervision because there aren't really existing resources that have narrative level inference. So this allows us to have these distant alignments between the narrative text, in our case, rock stories, which are 5-sentence common sense stories. And there's a set of heuristics that we use to make sure that these distantly supervised knowledge inferences are consistent given the overall story. And for that, we use a language model called GPT-2 that just gives us a probability for how likely the story is given a particular knowledge inference that we're considering. So before I talk more about the distant supervision, I wanted to dive into a little bit about the structure of atomic, the knowledge graph that we're using. So for this, then we have these event nodes that refers to a situation, for example, person X walks blank alone. And then we'll have these knowledge inferences that talk about relevant knowledge to this situation. For example, person X needing to be outside when they're walking alone, or person X being seen as tired. So for the distant supervision, we used two different approaches. One is a heuristic sentence level matching approach, where we look at how close in terms of unigram overlap, or looking at just single words, that the sentences in the narrative are with a particular event node in atomic that we're considering. So for example, we might get that Ella walked around the property as a sentence from the narrative is not very close to person X sends blank to a conference, but it is a lot closer to person X walks blank alone. We also tried model-based sentence level matching where we used the Comet model to generate a pool of relevant inferences for sentences in the narrative. So to enforce narrative level coherence, then we have this step where we look at the language model probability of all of these distantly supervised inferences that we've gotten. And for that, we're able to prune out some less relevant inferences that made it into the distantly supervised pool. For example, making sure that we include inferences like person X wants to fix the problem, but we remove inferences like person X wants to listen to music, which isn't related to the story that we have here. So we also wanted to make sure that we could capture narrative level information in the common sense models themselves. And for this, we looked into semantic and episodic knowledge, which we get from episodic and semantic memory and Tolvin. And for semantic knowledge, that can be implicit general knowledge captured by pre-trained language models. For example, the difference between talking about an apple that we want to eat versus Apple the company, as well as access to full narrative or prior events in the narrative context. And we also looked at episodic knowledge, which relates to prior predictions made by the model, as well as prior events in the narrative. So this image here shows the full architecture of our common sense inference model, and I'll break this down and walk through it. So we're using conditional generation for inference prediction on the atomic knowledge graph, where given an input narrative, then we also take as input a particular relation dimension that we want to generate common sense inference for, and a sentence of the narrative that we want to generate an inference for. And as part of our inference model, then we have what we call recurrent memory, and this keeps track of all the prior inferences that were generated by the model. And we retrieve the top k inferences from the recurrent memory by looking at the cosine similarity, how close the embeddings of these inferences are, but between the embedded inferences and the hidden states of the model. We average the retrieved inferences, and then we have an update step where we're able to use this information within our model to generate the next inference. So to evaluate how well these different models were doing at the task of coming up with knowledge that's actually consistent across a full story, then we came up with a gold set of inferences using human annotators to judge whether or not they were actually relevant. So for each of these cases, with 3 annotators, we might look at an example, like person X wanted to see the film, person X wants to enjoy the party. And we use a majority vote where we decide that the gold label should be relevant if 2 out of 3 of the annotators at least agreed that it was. So this allows us to collect a set of 607 knowledge tuples for our gold set with 313 unique common sense stories covered. And looking at the results, when we compare the different models, looking at Blue 1 and Blue 2, which is n-gram overlap metrics, as well as an NLI model that looks at how many contradictions there are between the inference and the story, then we found that across these metrics that using paragraph level information was helping. And also in our human evaluation, when we gave them a Likert scale with 5 different labels for how plausible an inference would be, we found that using the recurrent memory led to more inferences that are plausible, that are relevant to the story, but are more implicit and don't actually just repeat information that was already in the story, as well as more generally true or true inferences. So this leads to the question, does this actually translate to the real world when we're talking about stories? To look more into this, we looked at the Cosmos QA data set that includes personal blog posts. These cover the very complex kinds of common sense interactions that can happen when we're thinking about the real world versus narratives, including situational facts, reactions of people, temporal reasoning, counterfactuals, and cultural norms that might appear. And for this, we can see that the same kind of plausibility issues that were happening with the narratives also happen when we're thinking about these blog posts. So for example, in the blog post here, it says almost a month ago now, the radio station got struck by lightning. It fried the router and the cable modem. then our phrase level common sense model predicts person X wanted to be a good cook, or person X wanted to eat, probably because it's fooled by this keyword of fried, but we know that we're actually not talking about frying a router or a cable modem to eat, even though the phrase level model falls back on that. With the paragraph level common sense model, then we're able to predict that person X wanted to have better internet, or person X wanted to not be bothered, which is more on topic given the blog post. In this other example, we have a blog post that says, I posted a moment ago regarding a girl I asked out. She said that she would like to do something, but work made it difficult. That was a couple of weeks back. So here we can see that the phrase level model has some temporal issues where it says person X will get married or person X will get a divorce, which is plausible far in the future, but less plausible is the very next thing that will happen. Versus the paragraph level model predicts person X will be asked out or person X will get rejected. So now that we know that this is possible to use when thinking about online narratives, we can see how using common sense reasoning will impact issues where online narratives are weaponized to de-enfranchise vulnerable communities and propagate toxic behavior, as well as identifying the kind of tools used by authors of disinformation to spread propaganda online. In particular, next, we'll be talking about measuring toxicity of online narratives, using reasoning over these narratives, but I wanted to pause here to see if anybody had questions about the earlier part of the talk. Okay.
I had like a quick question. Sorry, I didn't raise my hand.
Yeah.
In the part when you were like evaluating like how good your inferences were, they were like long-term inferences, and you were using some neural net model to evaluate like how good they were, sort of. Is that neural net model, like how is it doing the long-term inferences, or is it just using totally different techniques? Or like that neural net has to have some understanding of like common sense?
Yeah. Yeah, so we're using neural nets to generate inferences. That case, we were assessing them with the story as part of the context. So we're seeing how likely is the story when we use one inference versus another inference.
So the neural net's like kind of able to evaluate inferences but not produce them, and that's in what you guys are doing is producing them.
Right.
Okay, awesome, thanks. That makes sense.
Yeah, there's a bit of a connection between the two, but yeah, it is. We did find that it was better at doing evaluation than generation.
Great, thanks.
Okay, so for this next part, then we want to look into using reasoning for understanding online toxicity, which has been an enormous problem with this kind of behavior cropping up on online discussion forums like Reddit and Twitter. And there's a number of issues that come into play when we think about toxicity of narratives, where it's not as simple necessarily as a binary thing between it being toxic or not being toxic, but there's also a dependence on who the audience and speaker perspectives are, and what role can discourse understanding play in determining toxicity of online narratives. So in the past, a lot of work on toxicity classification focused on a binary framework, including the Google Perspective API model, where given a social media post, like a tweet, then a black box toxicity detection model will predict a label of either being harmless, not toxic, or being toxic / hate speech. However, problems can arise with thinking of it in this way, including the fact that there's severe racial bias in hate speech detection data sets and models. For example, given a tweet shown here, which has a benign underlying meaning and is written in African American English, then a binary toxicity model assigns a label of being toxic while a tweet with the same kind of meaning that doesn't use particular keywords ends up being labeled as a harmless tweet. And this is because this toxicity classifier was trained on text-only annotations and doesn't have information about background of who is speaking, including the fact that they're speaking in a particular dialect. So when we looked at proportions of toxic tweets in existing Twitter toxicity data sets, then we found out that a large proportion of African-American English identified tweets were being labeled as being toxic versus white aligned tweets. And this filters down into machine learning models where they're also learning these kind of biases and leading to higher rates of misclassification of harmless African-American tweets as being offensive. Which leads to a real risk of de-enfranchising minority groups, the very groups that are commonly targeted by this hate speech, by models that were originally proposed to help people and have this positive impact. So we can see that binary hate speech detection is not enough. And the work that we did was to propose social bias frames, which uses a more nuanced perspective on toxicity, taking into account the fact that there are a lot of different aspects that come into play when we think about toxicity online, including who the speaker is and who the audience is of a particular social media post. This also allows for more interpretability of toxicity systems, where we can see it's actually making this decision for using these various reasonings and implications versus just knowing that it generated a label, but we don't really know why it had signed this particular label or where that label was coming from. So in the social bias framework, then given a post like the one shown here that says we shouldn't lower our standards just to hire more women, then instead of just having a binary label of is this offensive or is this not, then we also look into, was this intentionally offensive? Maybe in this case. Does it contain any lewd content? No. Is it targeting an individual or group? In this case, we can see that it's targeting a group, and the group is women. And there's this underlying implication that women are less qualified than men. We also have a category for whether or not the post is using in-group language. So we can think about combining these kinds of more nuanced formalisms and frameworks for toxicity detection along with common sense models over narratives to identify malicious authors, as well as common tropes or tools that these authors use when targeting people online. But this also raises the question of how can we detect authors of disinformation? So that's what I'll be talking about in the next part of the talk, but I will pause again if anyone has questions over the previous section.
If anyone has a question, you want to raise your hand, or you can speak up.
Hey, hi. So I have a question. So you mentioned that so inferences such as women are less competent than men. So is that like a human inferred? Like how do you get those annotations in this frame style?
Yeah. So those were all annotations that we got from human annotators who were reading the posts and then labeling based on the various dimensions that we had in our framework.
Right. Thank you. So this is indeed incorporating the biases of the annotators themselves subjected. So can there be more multiple inferences because there are so many annotators? For the
Yeah,
same.
definitely. And there's definitely going to be some posts where there might be more or less room for interpretation as well. There might be cases where it's ambiguous whether or not it's even toxic, and there might be a lot of disagreement between annotators based on what their backgrounds are over what's implied or whether even they consider it being toxic. But yeah, there's definitely a large, potentially large pool of implications that could come just looking at a single post.
Okay. So is there a method of pruning those inferences that you have employed?
We looked into that in the paper a little bit, because yeah, the simplest approach is just to think of whatever is most probable by a language model when thinking about generation, but that's not necessarily, that's very going to be somewhat biased itself based on whatever data the language model is trained on. So you could think of, generating a pool of inferences and then, having some kind of second step, either a human in a loop step or thinking about another model where, depending on the situation, you might want to choose one over the other. Or you could just consider multiple depending on the context.
Interesting. Yeah. Thanks a lot.
Okay, I think we
So
can keep
next I'll be, oh, are there any other questions?
No, I was just saying let's keep going forward.
Okay, yeah. So next I'll be talking about measuring factuality of generated and human written text, including defining what makes a summary true to a source and looking more into, are there particular errors or shifts in factuality that are easier to detect than others when we're thinking about online narratives or other kinds of narrative text, as well as what the dimensions of factuality are when it comes to thinking about surface level faithfulness of text versus more deeper meaning in terms of faithfulness. So we did an investigation looking at summarization, and we looked at summarization in particular because that gives us a good factual grounding where we have a source text like a news article or a chit chat online, or as shown here, part of a science paper. And then we have an output summary that captures salient facts or important parts of our original source. And within the field of summarization, then summarization models have been increasingly good at generating convincing text that looks like something a human would write. For example, the summary shown here that says a device called the Crow Box could enable bird watchers to make money from their hobby, as well as watch birds develop new skills. However, when we look closely at this, then we see that a lot of parts of the summary are actually just extracted from the original source, and there are a number of errors within the parts that are generated extractively from the model, including it starts talking about bullied crows, even though this didn't appear in the actual source, as shown here. Other issues might arise when we're thinking about factuality of summaries. So in this example, it says the solar system has landed in the US state of Ohio. We can immediately fact check this ourselves using common sense, because we know solar systems don't land on states. However, the model doesn't have this kind of reasoning or information to know that the original reference summary is actually referring to a solar powered plane and not to a solar system. There's also a lot of errors relating to locations, and sometimes models will say that somebody said something that they didn't and generate false quotes. And this has a wide-ranging impact when we think about the factual errors generated by these models, where they could propagate to social media as well as to scientific research. So a lot of the prior work looking at this, including our work later this year at EACL, looked at how we could improve factuality of models given established metrics, but it's not really clear whether or not these metrics are actually able to measure factuality. And for that, then we looked into commonly used generation metrics to see whether or not they were actually measuring factuality, including keyword overlap metrics, like n-gram-based metrics. And as we see in this example, where we have an article, if we measure the Rouge score of this article, then we find that there's actually a higher Rouge score assigned to the factually incorrect summary versus the factually correct summary. We considered other metrics like contextual similarity metrics, for example, BERT score that looks at how close the embeddings of a source are to the summary. And recently proposed metrics that use these proxy objectives for coherence, as well as potentially factuality, including ones focused on the closed task where you're predicting what fills in the blank, and question answering metrics. So our proposed framework is a metric for factuality metrics, a meta-evaluation of these metrics, where we came up with a set of conditions for what makes a good factuality metric, including that boundedness, where we expect that a generated summary should have a score that's lower to or lower than or equal to the score for the reference summary, and random summaries being a lower bound on the generated summary. Just looking to sensitivity, we're going to see how sensitivity metrics are to changes in the factuality of a particular text. So for this, we should expect that a summary with I errors has a score that's higher than or equal to a summary with I+1 errors. And for our sensitivity analysis, then we looked at the correlation between these metric values for different summaries and the factuality level of that particular summary. For our third condition, we looked at robustness. So we wanted to see if these metrics can capture different kinds of errors or whether they're just focused on errors in entities, for example, people's names or locations, as well as we considered pronoun errors, negation errors, sentiment errors, and false quote errors. And we looked at generality, so to see whether the metrics worked across different domains, including news and dialogue. Finally, I looked at human correlation to see if the metrics scores align with the kind of decisions that would be made by actual people when thinking about how factual text is. So stepping through a few of the different metrics that we tested SUMA QA, was one of our QA metrics, where given a source document, then we generate a question answer pair. And then we have a QA system that, given a generated question and a candidate summary that we want to evaluate, the QA system predicts an answer, and we can see how well this lines up with the actual gold answer for that generated question by looking at the F1 score between the predicted answer and the gold answer, as well as we look at the confidence of the QA system when making a prediction. And we aggregate that across all of our generated question answer pairs. We tried another variation on the QA framework, which is very similar, but in this case, we're generating question answer pairs from the candidate summary instead of the source, the source document. And then we looked at closed task metrics, including blank help, where we compare the score between predicting spans of text that were masked in the source document and using an NLU model that has the candidate summary as input to help predict these spans, and compare this against what if we didn't use that candidate summary to see how well it's actually helping. We use blank tune, which is a variation on this, and in this case, instead of using the summary as input, then we're using it to fine tune the model. And again, we're comparing that between using that candidate summary and having an untuned NLU model. And finally, we look at Rouge and Graham overlap metric, as well as BERT score for looking at contextual overlap. So the different data sets that we looked at for this investigation include XSUM, which has one-sentence summaries, CNN Daily Mail, which has multi-sentence summaries, and SAMSUM, which consists of multi-sentence summaries of dialogue, the other two being news data sets. So to conduct this meta-evaluation, we looked at a simulated error setting, in which case we inject a certain number of errors into a reference summary to simulate our various levels of factuality. And this allows us to conduct the sensitivity analysis, where we look at whether or not the metric's actually able to capture these different levels of factuality. We also look at generated errors to see how well this lines up with the actual distribution of the errors that are cropping up when we think about generations from models. In our particular case, we're looking at a T5 summarization model, which is just an encoder-decoder language model. And we do fine-grained human evaluation over these generated summaries to see not only what kinds of errors are cropping up, but how many errors are appearing. In our findings, we found that QA metrics seem to be most promising for detecting a wide range of factual inconsistencies, including entity errors versus more semantic kinds of errors that might be cropping up, like verb negation, false quotes. But in general, these are more challenging than entity-based errors for current metrics to detect. So how do we think about detecting these kinds of more semantic errors, which aren't captured by current models, but might be commonly used when we're thinking about disinformation? And for this, we've started to look into using common sense and been working on a new Commonsense Knowledge graph for tracking disinformation. And one thing to think about here is that a lot of the current Commonsense Knowledge graphs, like Atomic, contain very general common sense, which is helpful, but there also might be situational common sense that appears that will reveal more information about the intentions of disinformation authors, including when we're thinking about disinformation in health news, precautions for respiratory viruses versus airborne viruses, and what are the different implications of somebody in one particular social role saying something versus somebody in another social role, like a politician versus a military figure. So with this knowledge graph, then what we've been working on is given a news headline like the one shown here that says hydrochloroquine is why Uganda, with a population of 43 million, has only 15 COVID-19 deaths. We can understand not only is this misinformation, but we also know more about what the intention of the author is in writing something like this, in this case to imply that hydrochloroquine cures COVID-19. So that's where I see this work going forward. I want to thank all of my collaborators on these various projects, as well as all of you for listening to the talk, and feel free to ask any questions.
Let's first unmute ourselves and clap for Saadia. Thank you very much. Great talk. I see there's a bunch of hands going up. Dan Sheldon, do you want to ask your question first? Or was that clapping? Sorry, that wasn't hand raising. I got confused.
That was actually clapping, but I'll just say hi, Saadia. It's really good to see you.
Good to see you.
Okay, Brandon has his hand up and is not clapping. He did clap, but he's no longer clapping. So Brandon, you want to go ahead and ask your question?
Sure. Yeah, Saadia, thanks. That was awesome. I was wondering about the last project you're talking about for disinformation. Have you thought much about the author-specific or author-conditional factors into different types of knowledge? So when we're talking about disinformation, different sources might have pretty different axioms or assumptions about the world instead of being like general common everyone agrees. Is there a way to put that in or model that, or is that of interest?
Yeah, that's definitely of interest, and would be very interesting to explore. So we have the sources and we're looking into that now. It's kind of too early to have any sort of conclusions from that, but that's definitely something that we're considering.
Cool, thanks.
While folks are thinking up their questions, I'd like to ask one. So I think that what I'm thinking of lies kind of in the intersection of the two things that you've talked about. It's not quite misinformation, but it's almost like misinformation. I'm thinking of sarcasm. So, I find that NLP tools often really choke when somebody says the exact opposite of what they mean. To a point, the other day I was talking to a collaborator in NLP, and she said, oh, in NLP, we never consider that the text we're dealing with might just be saying the opposite of what the person actually means. So could some of the techniques you talked about be used to detect sarcasm? Imagine you're talking to an agent that's trying to help you book a plane ticket. And the agent says, I can save you, I'm thinking automated agent, I can save you $100 if you do a 5-stop trip or something like that. Right. And my response to be like, yeah, I'd love to do a 5-stop trip. Right, which is the exact opposite of what I mean. And the context won't quite tell me that, but there's some common sense to it that I don't actually love the 5-stop trip plus my tone. Could some of these techniques be used to detect sarcasm?
Yeah, definitely. And there's actually been work looking at integrating common sense knowledge into detection of sarcasm. I think it was at University of Southern California, where they were looking into using common sense models like the ones I talked about a little bit earlier, and that's been shown to lead to some improvement in detecting sarcasm. But there's definitely a connection here when thinking about the implications.
Okay, cool. Yair?
Hi, thank you for the talk. I have just a short question. So for the part about labeling toxic phrases, so do you know who labeled it? I mean, I think that would have a massive influence on, on the types of labels. I mean, as you mentioned, that there was a difference based on ethnicity and
Right.
eventually then gender. But I would imagine that's probably heavily biased by who labeled the data, right? So
yeah, very much so. In our work, when we were looking into racial bias, then one thing that we did look into was priming annotators to think not just from their own perspective, but from the perspective of other people. And we found that led to more equitable kind of labeling where they weren't mislabeling because of dialect as much. But it's definitely very important to think about backgrounds of annotators and how that plays a role. And a lot of times on crowdsourcing frameworks, and you're not necessarily going to get a very wide distribution in terms of demographics and who the annotators are, and that opens up, having people from very particular cultural perspective making decisions across different various cultures and dialects. And so that's something that we, yeah, definitely consider.
Thank you.
Great. David Jensen.
Hi, Saadia. Wonderful talk. Really, really nicely done. One of the promises, I think, of this work is that as common sense, databases, knowledge graphs of common sense get better and better, this systems like this will be easier, will be better and better. So we have this, I think we have a sense we're at the early stages now, but 10 years from now, we might have even better sense of this kind of common sense. Do you know of any work that has looked at kind of what effect that improvement might have, or what effect sort of injuring the knowledge graph of common sense that you have, what effect that has on the quality of results? Are we at a cusp right now where we've just become good enough, or is there, how much more running room is there to improve these things? That's, yeah, trying to trace where the performance comes from.
Yeah, that's definitely a very hot ongoing area of research where people are looking into evaluating these models and trying to better understand what they're actually learning and whether or not they're actually able to pick up on common sense in a more generalizable sense. And it seems like we're in very early days. Like they do tend to generate inferences in particular situations that seem like, oh, the model is learning common sense, but it's not clear how much is it actually learning common sense versus is it falling back on these kind of statistical biases. And there's definitely cases that we run into where it's clear that it's not actually learning versus just copying from a context. So there's a lot more work that could be done in this area, but it's an ongoing area of investigation.
Thanks.
Okay. I think that's all the questions that we have right now. So maybe let's clap for Saadia one more time.